We have so far worked out a quantum field theory for scalar fields, for free scalar fields. And we saw that this corresponds to spin zero field or spin zero particles because being a scalar, the field is unchanged under rotation and only spin zero has this property. But remember that as a guide to build our quantum field theory, we are trying to explain what's happening or to predict what's happening when we collide an electron with a positron, which annihilates and then creates a pair of muon-antimuon. And in these particles, represented in this Feynman diagram here, none of them have spin zero. So we have fermions, the electron and the positron, they have spin 1/2. We have the muon and the antimuon, which also have spin 1/2. And we have the photon, gamma, which is the mediator of the interaction and has spin 1. So we need now to incorporate spin 1/2 and spin 1 into our theory. We are going to do that first with spin 1 because that's easier, and later on we will work out quantum field theory for spin 1/2 particles. But first we will recap some properties which you have seen earlier and which connects the spin with how the object transforms under rotation and how it is encoded as a Lorentz object, which will then be used to build the Lagrangian, which at the end must lead to an action which is Lorentz invariant, so which is a scalar. So for a spin 0, the only possible projection is also 0. We know that such an object transformed under rotation as a scalar, so it is unchanged. And as rotation are part of the Lorentz transformation, this means that the Lorentz object which corresponds to spin 0 is the Lorentz scalar. So it's not only unchanged under rotation, it will be also unchanged under boost. In the case of a spin 1/2, we have two possible projections, plus and minus 1/2. The corresponding object transforms as a 2-spinor, and that's different than a 2-vector, as you already know. For instance, when you do a rotation of 2 pi, a vector comes back identical to itself. However, in the case of a 2-spinor, we need a rotation of 4 pi to get the spinor coming back identical to itself. And the Lorentz object which encodes this property for rotation, as we will see, is a 4-spinor. So it will have 4 components, not only 2. Finally, a spin 1 has 3 components for the spin, plus 1, 0, or minus 1. And it transforms as a Euclidean 3-vector, and the simplest Lorentz object which will encode such property for the rotation is a 4-vector. Finally, it is informative to see how much degrees of freedom we can encode into these different objects. So in the case of a scalar, we have just one number, so the number of degrees of freedom is just 1. In the case of a 2-spinor, it's 2 because we have a spin up and a spin down component. And in the case of a 3-vector, it's 3 because we have 3 degrees of freedom associated with the 3 directions of space, x, y, and z. Of course, it's not a coincidence that we have one projection of the spin ms for a scalar and that we have only 1 degree of freedom. Similarly, we have 2 projections for a 2-spinor and we have 2 degrees of freedom, and 3 projections for a 3-vector and 3 degrees of freedom. But then how does it translate into our Lorentz objects? So for the Lorentz scalar, we also have only 1 degree of freedom, so all is fine. For the 4-spinor, however, we in principle have 4 components, so perhaps we have 4 degrees of freedom, and that's something we will have to keep in mind. But I leave a question mark because we will come back to this problem later on when we will discuss spinor fields. In the case of vector fields, we know that a 4-vector has 4 components, 1 for time-like component and 3 for space-like components. So that's fine because that means we have enough degrees of freedom to encode a spin 1 particle into a 4-vector, a Lorentz vector, because we have more than 3 degrees of freedom. However, that also means that we have an additional redundant degree of freedom, which we will have to take care of when we will discuss a vector field. The last comment is that our photon has spin 1, but despite the fact that it has spin 1, it has only 2 degrees of freedom, because the photon can only be found with ms equal +1 or -1. You can't find a photon with a projection of the spin ms equals 0. And that's because it's a massless particle, and therefore it always moves at speed of light. In other words, there is no rest frame for the photon. There is no inertial frame in which the photon will be at rest. And that, as you might have seen earlier, removes 1 degree of freedom for the photon. So we will now generalize what we have seen for scalar fields to the case of vector fields. We will leave the case of spinor for later because it's a bit more complicated. However, we will have massive vector fields, so we will have a mass for the field which is not 0. In that case, we will have 3 degrees of freedom for the spin 1 particle. Eventually, at the end, we will recover quantum electrodynamics by taking the mass of the vector field going to 0. In principle, we are not allowed to do that because the photon and a massive vector field do not belong to the same group. However, that will give us the correct result, the correct equations for quantum electrodynamics, so that's going to be the approach we will take in the following lectures.